Hello and welcome back to the channel where we are reviewing the Salvadori's textbook Structure in Architecture. This video is about chapter 10 and that is all about grids, plates, folded plates, and space frames. So let's take a look at the first subsection, and that is load transfer in two directions. So the structural elements considered so far that we discussed in the previous chapters have in common the property of transferring loads in one direction. A load set on a cable on a beam is channeled to the supports along the cable line or the beam axis. In arch, a frame and a continuous beam produce the same type of one-directional load dispersal. These structures are labeled one-dimensional resistant structures because they can be described by a straight or curved line along with the stresses channel the loads. So one-dimensional resistant elements may be used to cover a rectangular area, but such an arrangement is often impractical and inefficient. So, for instance, a series of beams, all parallel to one of the sides of the rectangle, serves this purpose, but a concentrated load on such a system is carried entirely by the beam under the load, while all other beams are unstressed. So the load transfer occurs always in the direction of the beams, and the loads are supported by the two walls at their ends, which while the walls parallel to the beams remain unloaded. So this may be a proper solution when unloaded walls are needed for functional purposes, but it becomes inefficient when all the walls enclosing the space can be used to support loads. And please refer to the image here. You can see the concentrated load on one-dimensional system of beams. And we are moving to the second subsection of chapter 10, and that is rectangular beam grids. So you can see if two beams of equal length crossed at right angles to each other are loaded at their intersection, both will deflect the same amount and share the load equally. The load is therefore distributed along the span of each beam in two perpendicular directions, or what is referred to as two-way load dispersal or two-way action. If two identical simply supported beams at right angles to each other placed on top of the other are connected at their intersection and a concentrated load is applied there, the load is transferred to the supports at the ends of both beams and dispersed in two directions. So please refer to the images. You can see here the two-way dispersal by different beams, how that works. So two beams at right angles must deflect by the same amount as, at their intersection, even if they have different lengths or different cross sections. However, a greater load is required to deflect a stiffer beam by the same amount as a more flexible one. So the stiffer beam will support a greater share of the load than the more flexible beam, and the loads on the two beams will not be equal. The stiffness of a beam under a concentrated load is universally proportional to the cube of its length. So if two beams of identical cross sections have spans in the ratio of 1 to 2, the stiffnesses are in the ratio of 8 to 1. And consequently, the short beam will carry 8/9 of the load and the long beam 1/9 of the load. Please refer to the images here. So the sharing of one concentrated load between two beams may be extended to a series of concentrated loads by setting beams in two or more perpendicular directions, one under each load. So the intersection points must deflect by the same amounts. And if three equally spaced shorter cross beams of equal stiffness supported, the middle beam deflects more and takes a greater share of the load than the side beams. The greater dispersal in the direction of the shorter, stiffer span is evident. The two long sides of the boundary support more than 90% of the total load. With a long beam 8 times stiffer, the long sides still carry about 65% of the total load. The loads tend to move to the support along the shortest possible path, and two-way action vanishes as soon as the ratio of the long to short sides of the rectangle, which is referred to as the aspect ratio, is greater than 1.5. So again, please take a look at the graphics here. You can see two-way dispersal of three loads. And also, a better interaction of the two beam systems is obtained by weaving the beams so as to have their relative positions change at each intersection. In this case, the grid system is capable of giving support from both below and above. A beam moving up is pulled down by the cross beam set above it, while a beam moving down is pushed up by the cross beam under it. In practice, this behavior is obtained by means of welded or bolted connections between the beams of steel grids and occurs naturally in reinforced um, concrete grids due to their monolithic construction. So again, there is an example, and that is the roof of the National Gallery in Berlin, Germany, by the architect Mies van der Rohe. Please refer to the images. You can see the rectangular grid. You can see how uplift of upper beam of grid works, and you can see the woven grid as well as the National Gallery in Berlin. You can see the roof there and how it's constructed. So rigid connections between the beams of the two systems introduce another structural action in the grid. When two perpendicular beams connected at midspan are deflected by a concentrated load at their intersection, their midspan section move downward but remain vertical because of symmetry. When the intersection of the two beams does not occur at midspan, the beam sections deflect and rotate, and the continuity introduced by the rigid connection transforms the bending rotation of one beam into a twisting rotation of the cross beam. The stiffness of the grid is greater when the beams are rigidly connected than when they are simply supported over one another. And this indicates that the twisting mechanism is capable of transferring part of the loads to the supports and produce smaller displacements in the grid. Again, refer to the images, how that works. You can see the grid action with twist. And more complex interaction occurs when intersecting beams of a grid are firmly connected. Under load, members are at right angles to each other, and they're not only deflected symmetrically in the center point, but become twisted away from the center due to the deflection of the opposite direction beams. And the grid is made stiffer through the twisting action if the members did not interconnect and could move independently. The stiffness, however, comes at a higher fabrication cost due to many connections. And we are moving to the next subsection, that is skew grids. An additional saving in floor depth may at times be achieved by the use of skew grids, in which the beams of the two systems do not intersect at right angles. You can see there are images here, how that is described and how that is connected. And you can see the skew grid, and you can see the reversal of curvature in skew grids. So in case of rectangular areas with one side much longer than the other, most of the beams of a skew grid span equal distances, and the loss of the two-way action is substantially reduced. Moreover, the beams diagonally across the corners of the rectangle, shorter and stiffer than the other beams, give stronger support to the beams intersecting them. For loads concentrated around the corner of the plate, because of these stiff supports at ends of the longer beams tend to lift up at the corners. Keeping them attached to the walls requires a downward force, creating a reversal of curvature in the longer beams, which behave very much as if they were fixed rather than simply supported at those ends. And you can see that in this graphical representation. So since a beam with a fixed end has a load carrying capacity for uniform loads 120% greater than an identical simply supported beam, skew grids have greater structural efficiency. And please take a look at the facade of the Seattle Public Library. You can see that the facade wraps the building with a folded set of planes, each surface constructed as skew grids. And there is a beautiful picture of that. So we are moving to the next subsection of the chapter, and that's plate action. Two-way action of beam grids is due to the pointwise connection of the two beam systems at their intersections. Such action is even more pronounced in practice because the openings in the grid are plugged with slabs or plates, thus making the roof or floor an almost monolithic structure. The advantages of an entirely monolithic structure having two-way action at all points would be even more pronounced. And please refer to the image here. You can see the equivalent grids in plate action. So a plate or slab is a monolithic structural element or relatively small depth covering an area which at first shall be assumed to be rectangular, and a strip or plate parallel to one side of the rectangle may be thought of as a beam acting in one direction, and a strip at right angles to the first may also be considered as a beam. And since the two perpendicular beams act together, bending of one produces twisting in the other. If the members of a grid are assumed to be infinitely narrow and very close to each other, a solid plate results. The resulting monolithic action creates two-way action even more pronounced than in comparable beam systems. The internal slab beams may be considered orthogonal or skewed, and you can see the images here. So the analogy with the beam grid shows that a plate under load will bend and twist at every point. Bending produces beam action, that is bending and shear stresses. Twisting produces torsional shears. Again, please refer to the images, how that is, how the forces are in conjunction with each other, and you can see the plate action. So a rectangular plate supported on four corners may be considered to consist of multiple parallel beam elements, such as these few here. So load carrying by twisting action characterizes plates and differentiates from beams and grids, since even welded grids cannot develop substantial twist and action. In this connection, it's interesting to notice that the plate twist is responsible for a good percentage of its load carrying capacity. For example, in a square plate uniformly loaded and simply supported along its four sides, twisting action is responsible for approximately 50% of the load transfers to the supports. In rectangular grid weak in twist, 90% of the load is transferred to the supports by beam action. So also it's interesting to see that it was noticed that a plate may be considered capable of developing grid action in any direction. This means that any point in the plate may be considered as the intersection of two beams of a rectangular grid system, and that any number of rectangular grid systems may be thought of as passing through a plate point. So the deflections of the plate explain visually the structural behavior of the plate. The center strips of the plate deflect very much as simply supported beams. At the corners, the two sides of the plate are compelled to remain horizontal by the boundaries, assumed capable of reaching both up and down. And the entire corner areas are stiff, the ends of which diagonal strips are thus prevented from rotating, and these strips behave as fixed end beams with a reversal of curvature at the ends, similarly to beam grids shown here. And please refer to the images. You can see the different types. So the next section that I would like to discuss is square plate isostatics and rectangular plate isostatics. So because a plate may be considered to consist of either a rectangular or a skew grid, the bending stresses will depend on the direction of the conceptual beam. There are two perpendicular directions in which these stresses are having maximum and minimum values. The principal stresses in these principal directions may be plotted as isostatics for a square plate and rectangular plate here. So along this, no twisting action occurs to transfer loads between the orthogonal lines. And please refer back to the images. You can see the deflections of a square plate supported along its boundaries and under uniform load. Also, you can see how the plate corners curl up, and you can see how plate corner hold down forces. So those images are worth noticing, and please take a look at them because they explain a lot. So shear reinforcement at plate corners. You can see here that there's shear stress at plate corners as well as the shear reinforcement at plate corners. Shear stresses are present at 45 degrees to the principal stress directions. And in a concrete plate, reinforcing bars are needed near plate corners to prevent diagonal shear cracking. Also refer to the image here. There's action in simply supported rectangular plate, and also the rectangular plate with sides carries a distributed loads, and the distributed reaction on the boundaries has a maximum values that's different on the long and short sides respectively. So please take a look at the images to visualize this concept. And we are moving to the next subsection, that's plate structures. So many of the plate shapes and different support conditions find application in construction, and that is mostly as floor slabs. You already know that. So The conditions of support may differ on the four sides of a plate. A plate may have two simply supported parallel sides and two fixed parallel sides. In this case, an increased rigidity of the long spans due to their fixity may compensate for a large aspect ratio. The plate exhibits two-way action comparable to that of a square plate with all sides simply supported. Please refer to the image. You can see the plate with opposite simply supported and fixed sides. And you can see plate with adjacent simply supported and free sides, as well as the corner balcony plate with fixed supports. So how that works. And again, there is a building showing the floor slabs of the building with inner core, how that is operated. And you can see that there are only perimeter columns that are required here. So circular plates. A circular shaped plate, simply supported by its boundary, behaves essentially like a circumscribed rectangular plate. Uh, if the boundary is fixed, it behaves similarly to a square plate inscribed within the circle. Ring slabs may be built to span the area limited by concentric outer and inner circular supports. As soon as the radial span of the slab is small in comparison to its average radius, two-way plate action under uniform load is considerably reduced, and the slab exhibits stresses of the same order of magnitude as those of beams spanning the radial distance between the two circular boundaries. Slabs may also be point supported in columns, either hinged or fixed to the slab. The connection between the columns and the slab must be designed to absorb the so-called punch and shear from the column and may require the use of capitals or an intermediate distributing plates called drop panels. In order to avoid capitals, shear connections of steel are used sometimes in reinforced concrete design to guarantee the transmission of load from the column to the slab. Slabs used in floors or flat slabs present the constructional advantage of smooth underside surfaces, which permit the unimpeded running of pipes, ducts, and other parts of the various mechanical systems required in the building. Please refer to the image here, and you can see the illustration of the punch and shear in a column-supported slab. Also, you can see the shear connection, how that works for the column in the reinforced concrete. A grillage of steel called a shear head may be used to transfer loads from columns to reinforced concrete slabs. Reinforced concrete slabs supported by steel or concrete columns are easily poured on plain forms. An additional saving in the formwork is achieved by pouring the slabs on the ground, one on top of the other, and lifting them to the top of the columns by means of hydraulic jacks. Also, buildings with a large number of floors have been built by this lift slab technique. Although there was a tragic construction failure at the Lambiance Plaza project in Connecticut in 1987 that resulted in curtailed use of this technique. So another popular technique for walls only, called tilt up, involves casting flat panels horizontally on the ground. The cured panels are then lifted and rotated by crane into a vertical position, serving as perimeter walls for buildings no higher than 2 or 3 stories. An important application of reinforced concrete slabs as both vertical walls and horizontal floor occurs in prefabricated panel construction. The slabs are fabricated and cured in a factory setting and then erected and joined on the site with savings in labor and construction time. particularly when the electrical and plumbing systems are incorporated in the panels already. Inclined slabs are used in roof designs as the sides of gable roofs or the sloping sides of north light roofs, in which the higher boundary of the slab is supported on a truss. The vertical trusses, the truss elements are light and permit to use of large glass surfaces, usually exposed to the uniform north light required in factories and artist studios. Inclined slabs are often used in storage bins and other components of industrial buildings. Such inclined slab carries some of the load by tension or compression down their slope and some by plate action in a direction perpendicular to the plate. And we are moving to the next subsection, and that's ribbed plates. So the structural efficiency of plates is reduced by the linear stress distribution across their thickness. Only the top and bottom plate fibers at the most stressed point in the most stressed direction develop allowable stresses. In case of beams, this inefficiency is remedied by locating as much material as possible at a distance from the unstressed neutral axis, thus obtaining I and T sections. The same remedy can be adapted to plates. Please refer to the iconic image of Montreal Expo 67. That's the Habitat condominium. And this is how it is constructed. So it's the key feature of this complex is the multi-level dwelling units, each with an individual garden terrace on the roof of the unit below. So this is quite interesting, and I highly recommend to look at that in the textbook. So you can also see the images of the north light roofs, how the inclined or vertical slabs are put together, as well as the inclined slabs in storage bins. So concrete slabs may be arranged to form pyramidal storage bins. Loads in such inclined slabs are carried by tension or compression in the slope or by plate action perpendicular to the plate span. Also, you can see the ribbed slab here, as well as the concrete and tile floor, how that is constructed. An economical solution of the slab problem for rectangular floors with relatively small spans is commonly obtained outside the US by a mixed structure of reinforced concrete and tiles. The hollow tiles are set on a horizontal scaffolding of planks to create the formwork for parallel reinforced concrete ribs. Steel bars are set between the tiles to reinforce the ribs and above the tiles to reinforce the slab. Concrete is then poured in between the tiles and above them. And you can see the image. In the US, the floors of steel buildings are often built by pouring a concrete slab on a steel deck, which is supported on steel beams and acts as both the formwork for and the tensile reinforcement of the concrete slab. So please refer to the image, and you can see that the steel deck is made of thin galvanized sheet steel, and through its wavy cross section introduces one-way ribs in the concrete slab. In composite action floors, a concrete slab is poured and rigidly connected to the top of steel beams. The beams stiffen the slab, which in turn acts as an upper compression flange for the beams. Also, you can see the composite steel beam concrete deck floor with wire mesh reinforcing. And you can see the shear studs and then the concrete poured on top of the steel deck with reinforcing. Waffle slab. To achieve two-way slab action and greater efficiency, a waffle grid of ribs may be created. Such slabs are economically formed by reusable steel or reinforced plastic domes set atop on a temporary formwork with reinforcing placed in the space between the domes. Here, please refer to the image. There is a beautiful Cleo Rogers Memorial Library in Columbus, Indiana, and that's created by the architect I'm Pei. A concrete slab ribbed in two perpendicular directions is called a waffle slab and is used to cover a rectangular area. When the sides of the rectangular area are substantially different, deeper ribs may be used in one direction, or in case of reinforced concrete, the two sets of ribs may have the same depth and be reinforced differently. Waffle slabs are obtained by laying steel or concrete plastic domes on a horizontal scaffold in a grid pattern, laying reinforcing steel bars between and above the domes, and pouring concrete between the domes to create the ribs, and above the domes to create the slab. The domes can be reused a large number of times. Please take a look at the next image, and that's the isostatic slab. And you can see the plan here. So Italian engineer Pierluigi Nervi pioneered new construction techniques in concrete, including slabs with ribs curved along isostatic lines. To create the ribs, Nervi fabricated permanent ferrocement shell forms from reusable master molds, into which reinforcement was placed and then filled with concrete. And you can see the beautiful papal audience hall at the Vatican, and that is constructed with the isostatic slab. Um, the appearance of a ribbed concrete slab may be enhanced by the suggestion of the Italian engineer Aldo Arcangeli to have curved ribs along the isostatic lines of the plate. Again, please take a look at the images. The pattern depends on the support conditions at the plate boundary and on the loads to be carried. So this, again, please look at the images. Two-layered concrete slab structures analogous to I-beams are obtained by pouring a concrete slab on a flat scaffold and then pouring it on a waffle slab. In each case, disposable boxes used instead of reusable domes to create the ribs or webs are lost in the process. Similar sandwich plates with high strength to weight ratios are obtained by inserting between two thin plates of plywood, gypsum, steel, aluminum, or plastic materials, plastic foam with good shear resistance. In such stressed skin panels, the plastic foam constitutes lightweight two-dimensional web, where the two plates develop the bending resistance of the sandwich. Such plates have good thermal and acoustical insulating properties. Sandwich plates of cardboard with honeycomb paper webs are used in many applications where a reduced dead load is essential, such as in aircraft structures and packaging. Styrofoam sandwiched between plywood or oriented strain board sheets, OSB, known as structurally insulated panels or SIPs, can be used as roofs and walls in buildings. And also steel plates constitute the webs of plate girders, deep beams used in bridges or other large structures. Their buckling resistance is highly increased by vertical and longitudinal stiffeners, which essentially reduce the length of the plate strips that tend to buckle. So we are moving to the next subsection, and that is strength reserve in plates. Plates are called two-dimensional resistance structures because two numbers are needed to define the location of one of their points. In a case of rectangular plates, these numbers are the distances of the point from each of the two sides measured parallel to the other side. One of the essential characteristics of two-dimensional structures is their high reserve of strength, which stems from two separate sources: stress redistribution and membrane action. I will talk more about that in the next chapter. What is important to understand here? You can look at the image here where hinge lines of simply supported square plates are shown. So in a beam, stress distribution varies from a maximum tension on one surface to a maximum compression on the other. When the maximum stresses reach the yield strengths of the material, internal regions will yield until the whole cross-section yields and a hinge develops. And you can see the diagonal lines here. So when the plate has developed enough hinge lines to become a moving mechanism, it cannot carry additional loads. Distribution of stress in a beam can take place at only one or a few sections before failure occurs. In a plate, redistribution takes place along the entire line of sections. So the reserve of strength is generally greater in a two-dimensional element like a plate than in a one-dimensional structure. The reserve of strength in a simply supported square plate um, under uniform load is 80% as against 50% in a simply supported beam. And please refer to the images. You can see the cable action due to longitudinal restraint of beam ends, and you can see beam bending lateral displacement, and you can see tension in restrained beam. And there are formulas that I would like you to actually be aware of. A rectangular plate simply supported along two opposite sides and free along the other two behaves very much like a series of parallel beams. If its simply supported sides are free to move relative to each other, the plate cannot develop cable stresses. Cable stresses will be developed only if the two opposite sides are restrained from moving. The surfaces of plates deflecting under loads are in almost all cases non-developable. The middle plane of the plates much stretch to acquire such deflections, and stresses are developed in the middle plane of the plate capable of carrying some load by a membrane action. Membrane action is the two-dimensional equivalent of one-dimensional cable action. It is the action developed under load by a very thin sheet of flexible material, such as cloth. And yes, we will talk about membranes in the next chapter, chapter 11. So please take a look at the video that I posted as well. We are moving to the next subsection, that is folded plates. So what is interesting to see here, the structural efficiency of plates can be increased by stiffening them with ribs, thus removing some of the material from the neighborhood of the middle plane of the plate and increasing its moment of inertia. The same result may also be achieved with folding the plate. A sheet of paper held along one side cannot support its own weight. Its minute thickness does not give a sufficient lever arm to develop an internal couple capable of resisting the bending stresses. Folding the paper sheets bring the material of the cross section away from its middle plane and increases the lever arm of the bending stresses, which becomes comparable to the depth of the folded strips. Um, so folded plate action is a combination of transverse and longitudinal beam action. And let me show you how that acts in the paper. So if we take just like a piece of paper, it's not gonna hold. But if we bend it and hold like this is definitely going to work. So the reaction of the transverse strips at the folds may be split into components. For example, in a triangular truss, would load the slab in their own planes. So these longitudinal reactions are carried to the end frames by the slabs acting as deep rectangular beams. So the load is first transferred to the folds by beam action of the slabs in the transverse direction, and then to the end frames by longitudinal beam action of the slabs. Um, so you can see images. There is a section of rectangular beam equivalent to folded plate. And you can see the folded plate roof, how that is constructed, as well as the folded plate forces, how they are, the direction of the folded plates. A uniformly loaded roof consisting of a large number of folded plates develops the same deflections in all the slabs, except those near its internal and external longitudinal boundaries. Um, to avoid overstressing, the exterior slabs may be stiffened by additional vertical deep beams at the boundary. The one-sided lack of support of the exterior slabs is thus compensated for by the supporting action of the boundary beams. Please again refer to the images. You can see the transverse continuous beam action in folded plates, how that acts, and you can see the action detail here. So folded plates can come in a variety of cross sections. Some of them, excuse me, are illustrated above. The exterior final fold of a plate will have a different transverse stiffness than its interior counterparts. To help equalize the transverse slab actions at the outer edges, one approach is to add a vertical deep beam to function as a stiffener. And please refer to the images again. You can see the polygonal folded plates, how that acts. So in both radial and linear arrangements, they behave similarly to arches and must be restrained against lateral thrust. The circular form is compressed circumferentially by tie rods. The linear form is stabilized by a cross tie. At the center of the assemblage, a hinge develops because the small depth at that point can't support bending stresses. We are moving to the final subsection of chapter 10, and that's space frames. So the two-way action of a rectangular or skew grid system can be used to span large areas by substituting trusses for beams. The rectangular or skew roofs are obtained and they exhibit a minor amount of load carrying capacity through twisting action because of the small twisting resistance of the trusses. So a substantial increase in the twisting action of such roofs can be obtained if panel points of parallel and perpendicular trusses are connected by skew bars. The truss systems become triangulated in space, and their behavior is analogous to that of thick plates made out of spongy material rather than to that of grids. Such triangulated space trusses called space frames are often used as roof structures to cover large areas because they consist of a large number of identical bars of a few different lengths and may be built in a variety of patterns whose lace appearance has high aesthetic content. And you can see the Air Force Academy Chapel in Colorado Springs. That is designed by Walter Nitsch of SOM, and that was completed in 1962. So now it is a U.S. National Historic Landmark, which got this designation in 2004. Creased paper barrel. A folded paper structure of this type is capable of carrying a considerable load if the longitudinal borders are prevented from displacement and the load is uniformly distributed along its surface. Also, you can see the rectangular space truss and you can see the space frame. So the introduction of skew bars increases the twisting resistance of a rectangular space truss to create a space frame. The behavior of a space frame is analogous to a thick plate made from a spongy material. And please refer to the images. You can see how actually it is constructed. So you can also see the slotted and screwed connectors. You can see mirror system and you can see Tomoe unit truss. And that's the prefabricated connectors and they are used at the intersections of truss members in space frames. The intent of all these systems is the reduction in cost and increase in construction speed through simplicity and standardization of the connectors and bars. Each proprietary system manufacturer has its own particular approach to achieve these objectives. And here you can see the Takenaka truss, and you can see the Du Chateau space frame element. Also, there are images of the details of PG space frame bar and support. The PG system consists of a tension rod in the center of the pipe. The pipes are connected to hollow spherical connectors and the tension rods bolted from the inside. By pre-tensioning the rods in the entire assembly, the system can be constructed on the ground and then lifted into place by crane. So please refer to the images. You can see the Javits Convention Center in New York City, as well as the Ferrari World Abu Dhabi, how that is constructed. So, and this wraps up our chapter 10. Thank you so much for watching. I will see you in chapter 11.